This evening, we are going to set out on an exploration of a topic that might sound deceptively simple on the surface, yet it stands as one of the most intellectually challenging and mind-bending concepts in the entire realm of science. We are talking about the light year. It is highly likely that you have heard this specific term thousands upon thousands of times before. Scientists and astronomers utilize it constantly when they are discussing the cosmos. However, here is the thing that the vast majority of people do not fully realize. When you actually comprehend what a light year truly signifies, when you genuinely grasp the sheer scale of the distance it represents, it fundamentally alters the way you view the universe. It is not merely a large number. It is a distance so incredibly vast that it challenges our human ability to even comprehend it. And by the time we reach the conclusion of this journey, you are going to understand exactly why astronomers require this specific measurement and why absolutely no other unit of measure would work in its place. Before we proceed any further into this deep dive, if you find this type of profound exploration interesting, leaving a quick like or subscribing really helps the channel to grow. It is a small action for you to take, but it makes a massive difference for me. Now, let us dive right in. Let us begin with a concept that is familiar to you. Distance. You understand distance in your day-to-day existence. You know exactly how far it is to drive to the grocery store, how far it is to your workplace, or the distance to the neighboring city. These are distances that you can relate to personally because you have traveled them yourself. You possess an intuitive sense of what they mean in terms of time, in terms of the effort required, and in terms of what you will see along the route. A kilometer is approximately the distance that you can walk in 10 to 12 minutes at a normal, steady pace. These measurements work perfectly well for our everyday lives. If somebody tells you that the store is 5 kilometers away, you know roughly how long it will take to drive there. You can picture the journey in your mind's eye. Perhaps you will pass a few traffic lights. Maybe you will see some familiar landmarks. The distance is concrete, and it is relatable. If someone says that a city is 200 kilometers away, you can plan your trip accordingly. That is approximately 2 hours of driving. You will want to fill up your gas tank and perhaps bring along some snacks. You might plan for a rest stop halfway through. These distances are human-scaled. They fit comfortably into our lives and our direct experiences. We have evolved to understand distances that we can walk in a single day, distances that we can see with our eyes, and distances that matter for our immediate survival and navigation. However, these measurements start to become incredibly awkward when we begin to talk about really large distances. The distance from New York City to Los Angeles is about 4,500 kilometers. That is still manageable as a number. It is roughly a 5-hour flight. People make that journey all the time. They cross the North American continent. They watch the landscape change from the East Coast cities to the Midwest plains, to the Rocky Mountains, to the Southwest deserts, and finally to the Pacific coast. The journey is long, certainly, but it is achievable. It is within human capability. You can imagine making that trip. The circumference of the Earth at the equator is approximately 40,075 kilometers. That is a big number, but it is still something we can work with conceptually. Early explorers sailed around the world, so we know it is possible to travel that distance, even if it takes months to do so. Ferdinand Magellan's expedition took 3 years to circumnavigate the globe from the year 1519 to the year 1522. Modern commercial flights can circle the Earth in about 45 hours if you were able to book connecting flights that went all the way around. The Earth is large from our perspective standing on its surface, but it is not incomprehensibly large. It is a finite object that you could, in theory, explore completely. But now, let us go bigger. The distance from the Earth to the Moon is approximately 384,000 kilometers. This is the point where normal measurements start to feel inadequate. 384,000 kilometers. That is hard to visualize in any meaningful way. It is not like driving across the country. It is not like sailing around the world. It is something completely different. There is no road to follow. There are no landmarks to pass. And there are no rest stops along the way. It is just distance. Pure distance across empty space. How would you even begin to travel that far? The Apollo astronauts took about 3 days to travel from the Earth to the Moon using incredibly powerful rockets that accelerated them to speeds of about 11 kilometers per second. That is about 39,600 kilometers per hour, which is roughly 400 times faster than highway driving. Think about that for a moment. 400 times faster than you have ever driven in a car. And even at that incredible speed, which required some of the most powerful rockets ever built, burning enormous amounts of fuel, it still took 3 full days. 3 days of traveling through empty void at speeds no human being had ever experienced before, just to reach our nearest celestial neighbor. And that is just to the Moon, the closest celestial body to Earth. The Moon is so close that you can see it with your naked eye. You can see details on its surface with a simple pair of binoculars. It is right there, hanging in the sky. And yet, it takes 3 days of rocket travel to reach it. When we start talking about the distance to other planets, to the Sun, or to other stars, kilometers become completely useless. The numbers get so large that they lose all meaning. They become abstract symbols on a page rather than distances you can relate to in any way. The distance from the Earth to the Sun is about 150 million kilometers. Try to visualize that. You cannot do it, can you? Your brain just sees it as a really big number, but you do not have any intuitive sense of what it truly means. There is nothing in your daily life that prepares you for a distance like that. Nothing in human evolution prepared us to think about distances this large. We evolved to understand the distance to the next water source, the distance to the hunting grounds, or the distance we could walk in a day. We did not evolve to comprehend 150 million kilometers. The Apollo spacecraft that took astronauts to the Moon traveled at about 11 kilometers per second on average. At that speed, it would take about 160 days, over 5 months, to reach the distance of the Sun. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at speeds up to 192 kilometers per second when it is close to the Sun, using the Sun's gravity to slingshot itself to higher and higher speeds. Even at this incredible speed, which is about 17 times faster than the Apollo spacecraft, the probe still takes months to complete its orbits around the Sun. And that star is close. It is right here in our cosmic neighborhood. It is the star we orbit. It is the source of all the light and heat that makes life on Earth possible. We see it every single day. It is familiar, and yet it is 150 million kilometers away. A distance so vast that even our fastest spacecraft takes months to traverse it. When we start talking about distances to other stars, even the Sun's distance becomes tiny by comparison. The Sun is our nearest star, and it is 150 million kilometers away. The next nearest star, Proxima Centauri, is about 266,000 times farther away than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is precisely why astronomers needed a different unit of measurement. Not because they like making things complicated, and not because they want to confuse people with big numbers, but because kilometers simply do not work when you are measuring cosmic distances. Using kilometers to measure distances to stars would be like using millimeters to measure the distance between countries. Technically, it is possible, but it is completely impractical. The numbers become so large they lose all meaning. They stop being distances and become just numbers. Abstract mathematical concepts that do not connect to anything in our experience. So astronomers came up with something different. The light year. But here is what you need to understand right from the start. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it is not. A light year is a measure of distance. It is the distance that light travels in 1 year. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. It is not just a speed limit that we have not broken yet. It is a fundamental law of physics. The speed of light is a constant, unchanging, the same everywhere in the universe. Whether you are on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Light travels at about 300,000 kilometers per second. Let me say that again, because it is important. 300,000 kilometers per second. Every single second, light travels 300,000 kilometers. This is not an approximation or an estimate. It has been measured with extraordinary precision. The exact value is 299,792.458 kilometers per second. But for our purposes, 300,000 kilometers per second is close enough. That is incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in 1 second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. It is a speed that is almost impossible to visualize because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience is an airplane. A commercial jet flies at about 900 kilometers per hour or about 0.25 kilometers per second. Light travels over 1 million times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour, or about 0.33 kilometers per second. Light is about 900,000 times faster. Even the fastest spacecraft we have built, the Parker Solar Probe at 192 kilometers per second at its peak, is still only about 0.064% the speed of light. It is moving incredibly fast by human standards, but compared to light, it is crawling. When you turn on a light switch, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in about 10 billionths of a second. That is so fast that there is no perceptible delay. As far as your brain is concerned, the light appears instantly, but the light did travel. It took time. It is just that the time was so short, you could not possibly notice it. When you see the sun in the sky, you are actually seeing it as it was 8 minutes and 20 seconds ago, because that is how long it takes light to travel from the sun to Earth. The sun is so far away that even light traveling at 300,000 kilometers per second needs over 8 minutes to cover the distance. This has an interesting implication. If something happened on the sun right now, If it suddenly changed color or dimmed or even exploded, we would not know for over 8 minutes. The event would happen, but the light carrying information about that event would still be traveling toward us. We would keep seeing the sun as it was, not as it is, for over 8 minutes. When you look at the moon, you are seeing it as it was about 1.3 seconds ago. Not much of a delay, but still a delay. When astronauts walked on the moon and talked to mission control on Earth, every word they spoke took 1.3 seconds to reach Earth. And every response from mission control took 1.3 seconds to reach the moon. This created a nearly 3-second gap in every exchange. You can hear this delay in the recordings. There is always this pause, this lag, because the radio signals carrying their voices traveled at the speed of light. And even light needs time to cross the distance between Earth and the moon. Light does not travel instantly. It has a speed, and that speed, while incredibly fast, is still finite. This is one of the most important discoveries in physics. Before the late 1600s, most people assumed light traveled instantly. You opened your eyes and you saw things immediately. So it seemed like light must be instantaneous. But in the year 1676, a Danish astronomer named Ole Romer made a careful observation of Jupiter's moons and noticed something strange. The times when the moons disappeared behind Jupiter varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Romer realized this was because light took time to travel the different distances. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation was not quite right because he did not know the exact size of Earth's orbit, but he proved that light has a finite speed. Today, we know the speed of light with extraordinary precision. We have measured it using lasers, atomic clocks, and sophisticated equipment. We have confirmed that it is constant, that it does not change depending on how fast you are moving or where you are. And we have discovered that this speed, this constant, is woven into the very fabric of the universe. It is not just the speed that light happens to travel at. It is a fundamental property of space-time itself. So a light year is the distance light travels in 1 year at this speed. Let us calculate that. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times 60 times 60 times 24 times 365, we get approximately 9.46 trillion kilometers. To be more precise, it is 9,460,730,472,580.8 kilometers. But for simplicity, we usually just say 9.46 trillion kilometers. That is what a light year is. 9.46 trillion kilometers. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that is the number we are going to try to understand tonight. Because understanding what a light year means is essential to understanding our place in the universe, the distances between stars, and the true scale of the cosmos. But first, we need to talk about what a trillion actually means, because most people have no intuitive sense of how large this number really is. We throw around words like million, billion, and trillion in everyday conversation. We hear about government budgets in the trillions, about billionaires, about millions of people, but we do not really understand the massive differences between these numbers. They all sound like big numbers, so we treat them as roughly equivalent. but they are not. The differences between them are staggering. 1,000,000 is 1,000 thousands. If you saved $1 every day, starting today and continuing without ever stopping, you would have $1,000,000 in about 2,740 years. That is a long time, but it is conceivable. You can imagine a timeline stretching back 2,740 years. That takes you back to ancient Greece, to the early Roman Republic, to a time when humans were already building cities, writing books, creating civilizations. It is a comprehensible span of time. 1,000,000,000 is 1,000 millions. Now, we are jumping up by a factor of 1,000. If you saved $1 every second, not every day, but every single second, you would need about 32 years to save $1,000,000,000. That is more than the time it takes for a generation to grow up. If you started counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you would be 32 years old when you reached 1,000,000,000. Think about that. 1,000,000 seconds is about 11.5 days. That is conceivable. You can imagine a period of 11.5 days. It is less than 2 weeks. But 1,000,000,000 seconds, that is 32 years. The jump from 1,000,000 to 1,000,000,000 is enormous. 1,000,000,000,000 is 1,000 billions. And here is where numbers start to completely lose their connection to anything we can relate to. If you counted to 1,000,000,000,000, counting one number per second without stopping, it would take you about 31,700 years. Let me put that in perspective. That is longer than all of recorded human history. Agriculture, the foundation of civilization, was only invented about 10,000 years ago. Before that, all humans lived as hunter-gatherers, moving from place to place, following animal herds and seasonal plants. Writing systems appeared about 5,000 years ago in Mesopotamia. The pyramids of Egypt were built about 4,600 years ago. The wheel was probably invented about 5,500 years ago. To count to 1,000,000,000,000, you would need to have started counting before any of that happened. You would need to have started when humans still lived in small tribal groups, when there were no cities, no nations, no written language, no agriculture, no permanent settlements. You would need to have been counting through the entire span of human civilization, through every invention, every discovery, every empire that rose and fell, through every war, every peace, every triumph and tragedy in human history. And you would still be counting today. And you would still have thousands of years to go before you reached 1,000,000,000,000. Let me try to make this even more concrete. 31,700 years ago, modern humans were living in the last ice age. We were using stone tools. We were hunting woolly mammoths and giant ground sloths. We had barely begun to spread across the globe. Modern humans had only recently left Africa and were just starting to populate Europe and Asia. There was no language as we know it today. No art beyond the most primitive cave paintings. No technology beyond sharp rocks and wooden spears. That is how far back 1,000,000,000,000 seconds takes you. And a light year is 9.46 trillion kilometers. Every single one of those kilometers is a kilometer. It is not an abstract unit. It is a real distance. The distance you could walk in about 10 to 12 minutes at a normal pace. And there are 9.46 trillion of those individual kilometers in one light year. 9.46 trillion separate distinct kilometer-long segments, each one the length of a walk to your local store. So when we say a light year is 9.46 trillion kilometers, we are talking about a distance that dwarfs anything in our daily experience. You can write it down, you can calculate with it, you can use it in equations, but grasping it intuitively is nearly impossible. Our brains simply did not evolve to handle numbers this large. We evolved to count the number of people in our tribe, the number of animals in a herd, the number of days until the seasons change. We can count to a few hundred, maybe a few thousand if we really concentrate. But 9.46 trillion, that is so far beyond our cognitive capabilities that it might as well be infinity. The best way to understand, light year is to build up to it gradually, starting with distances we can comprehend and scaling up step by step. We are going to take this journey slowly, moving from the familiar to the unfamiliar, watching as distances that seem vast become tiny compared to what comes next. Let us start with 1 light second, 300,000 kilometers. That is about the distance from Earth to the Moon and 3/4 of the way back. Think about what that means. Light leaves Earth, travels all the way to the Moon, which is 384,000 kilometers away, bounces back, and gets about 3/4 of the way to Earth. And all of that happens in 1 second. 1 single second. When astronauts on the Moon talked to Mission Control in Houston during the Apollo missions, there was a communication delay of about 1.3 seconds each way. The astronauts would say something, and Mission Control would not hear it for 1.3 seconds, because the radio signal traveling at the speed of light needed that long to make the journey. When Mission Control replied, their response took another 1.3 seconds to reach the Moon. So every exchange had a nearly 3-second delay built in. It is subtle when you listen to the recordings, but it is always there. There is this pause, this lag, because of the distance the signals had to travel, and because nothing, not even radio waves, can travel faster than light. 1 light minute is 60 light seconds, which is 18 million kilometers. The Sun is about 8 light minutes away from Earth, which is about 150 million kilometers. So 1 light minute is roughly 12% of the distance from Earth to the Sun. If you could somehow stand on the Sun, which you obviously cannot because it is a ball of plasma with a surface temperature of about 5,500 degrees Celsius, but if you could somehow stand there and look at Earth, you would be seeing Earth as it was 8 minutes and 20 seconds ago. If Earth suddenly exploded, you would not know for over 8 minutes. The event would happen, but the light from that event carrying the information about it would take over 8 minutes to cross the distance between Earth and the Sun. This has practical implications for space exploration that most people do not think about. When NASA operates rovers on Mars, there is always a communication delay because Mars is so far away. At its closest, when Earth and Mars are on the same side of the Sun in their orbits, Mars is about 32 million kilometers from Earth, which is about 2 light minutes. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance is about 400 million kilometers, about 22 light minutes. This means when the Perseverance rover is operating on Mars, every command sent from Earth takes between 2 and 22 minutes to arrive, depending on where Mars is in its orbit. And any data the rover sends back takes the same amount of time to reach Earth. You cannot drive a rover on Mars in real time like you would drive a remote-controlled car on Earth. The delay is too long. Instead, NASA engineers have to plan the rover's activities carefully. They analyze images from previous days, plan a route, write a sequence of commands, send those commands to Mars, and then wait. If something goes wrong, if the rover gets stuck on a rock or encounters an obstacle, they cannot react instantly. They have to wait for the information to reach Earth, which takes anywhere from 2 to 22 minutes. Then they have to analyze what went wrong, figure out a solution, write new commands, send those commands, and wait another 2 to 22 minutes for them to arrive. A problem that might take seconds to solve with a remote-controlled car on Earth can take an hour or more to solve on Mars. 1 light hour is 60 light minutes. That is about 1,080,000,000 kilometers, over 1 billion kilometers. That is a distance so vast that even imagining it is difficult. The planet Saturn, at its closest approach to Earth, is about 1.2 light-hours away. Saturn is one of the most distant planets you can see with the naked eye from Earth. A beautiful ringed world that has been observed since ancient times, and it is about 1.2 light-hours away. When the Cassini spacecraft was orbiting Saturn from 2004 to 2017, taking incredible close-up photographs of the planet and its moons, there was over an hour of delay between when it took a picture and when that picture reached Earth. The spacecraft would take a photo, convert it to digital data, transmit it as a radio signal traveling at the speed of light, and over an hour later, scientists on Earth would receive it. This meant that Cassini could not be controlled in real time. Engineers and scientists could not watch what the spacecraft was seeing and adjust its path on the fly, like you might steer a car or pilot a drone. Instead, they had to program entire sequences of commands days or weeks in advance, upload them to the spacecraft, and trust that Cassini would execute them correctly. If something went wrong, the spacecraft had to be smart enough to handle it autonomously, to recognize the problem and switch to a safe mode. Because by the time the problem was reported back to Earth and new commands were sent, over 2 hours would have passed. The situation could have changed completely in that time. One light day is 24 light hours, about 25,900,000,000 kilometers. We are now talking about distances where even our fastest spacecraft become incredibly slow by comparison. Voyager 1, the spacecraft that launched in 1977 and is currently the most distant human-made object from Earth, is about 24 light-hours away as of the year 2025. It has been traveling for nearly 50 years, moving at about 17 kilometers per second, which is about 61,200 kilometers per hour. That is incredibly fast by any human standard. At that speed, you could travel from one side of the United States to the other in about 2 minutes. And yet, after nearly 5 decades of constant travel through the vacuum of space with nothing to slow it down, Voyager still has not traveled one full light day from Earth. This is roughly the distance to the heliopause, the boundary where the Sun's influence ends and interstellar space begins. The heliopause is where the solar wind, the constant stream of charged particles flowing out from the Sun in all directions, finally slows down and mingles with the interstellar medium, the thin gas that fills the space between stars. Voyager 1 crossed this boundary in the year 2012, becoming the first human-made object to enter interstellar space. It was a historic moment, a milestone in human exploration. But it is still within one light day of the Sun. It is still, in cosmic terms, right here in our neighborhood. 1 light week is 7 light days, about 181 billion kilometers. Now we are in a region where nothing human-made has ever been, and nothing will be for decades or centuries to come. This is deep space, far beyond the planets, far beyond anything we have directly explored. Out here, the Sun would no longer appear as the overwhelming source of light and heat it is from Earth. It would appear as just a bright star, brighter than other stars certainly, but just a point of light in the darkness. If you were somehow out here floating in space at 1 light week from the Sun, you would see the Sun as a brilliant star. But you would also see thousands of other stars scattered across the black sky. You would realize, perhaps for the first time, that the Sun is just one star among many. 1 light month is roughly 30 light days, about 778 billion kilometers. At this distance, if you looked back at the Sun through a telescope, you would see it as just another star, not much brighter than many others in the sky. The solar system, with all its planets and moons and asteroids and comets, would be barely visible. Even with a powerful telescope, you might see Jupiter as a faint dot, but the inner planets would be lost in the sun's glare. Everything we think of as the solar system, all the planets we have studied and sent spacecraft to, all the worlds we know would be compressed into a tiny region around an ordinary star. And 1 light year is 365 light days. It is 12 light months. It is 52 light weeks. It is 8,760 light hours. It is 525,600 light minutes. It is 31,536,000 light seconds. See how quickly the numbers scale up? We started with 1 light second, which was already an enormous distance by human standards, about the distance from Earth to the Moon, and most of the way back. And we have been multiplying by larger and larger numbers. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And we are just now getting to 1 light year, 9.46 trillion kilometers. That is the distance light travels in 1 year, moving at 300,000 kilometers every single second for 365 days straight. And this is the fundamental unit astronomers use to measure the distances between stars, because stars are separated by distances measured in light years. And nothing smaller makes sense when you are dealing with these vast cosmic scales. So why do astronomers use light years? Because every other option is worse. Imagine if astronomers used kilometers for everything. Proxima Centauri is about 40 trillion, 140 billion kilometers away. That is awkward, hard to remember, and does not give you any intuitive sense of the distance. But if I tell you Proxima Centauri is 4.24 light years away, that is cleaner. You can compare it to other distances. If one star is 4 light years away and another is 40 light years away, you immediately know the second is 10 times farther. Light years also connect distance and time usefully. When you look at a star 4 light years away, you are seeing light that left 4 years ago. You are looking into the past. This connection becomes crucial when studying the universe. The speed of light is not just fast. It is the speed limit of the universe. Nothing can go faster. And this is not a technological limitation that we might overcome with better engineering or more powerful rockets. It is a fundamental law of physics built into the very structure of space-time itself. The speed of light is not just a speed. It is a cosmic constant that defines the relationship between space, time, energy, and matter. Einstein's theory of special relativity, published in 1905, showed that as objects approach the speed of light, strange things happen. These are not just theoretical predictions. They are observed facts confirmed by countless experiments over the past century. Time slows down for the moving object relative to stationary observers. This is called time dilation, and it has been measured directly. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate. The amount of energy required to accelerate it increases without limit as you approach light speed. To actually reach the speed of light would require infinite energy, which is impossible. The universe does not contain infinite energy. Therefore, nothing with mass can reach the speed of light. Let me explain why this happens. In our everyday experience, if you are on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour, relative to the train, someone standing on the ground would see the ball moving at 70 kilometers per hour. The speeds add. This seems obvious, and it works perfectly well for everyday speeds. But Einstein showed that this simple addition does not work when you are dealing with speeds close to the speed of light. If you are on a spacecraft moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light, at least from the perspective of someone watching you. But it does not. The light still moves at exactly the speed of light, 300,000 kilometers per second, both from your perspective on the spacecraft and from the perspective of someone watching you from outside. This seems impossible. How can the light be moving at the same speed for both observers when one observer is already moving at half the speed of light? The answer is that space and time adjust to keep the speed of light constant. If you are moving very fast, time literally runs slower for you from the perspective of a stationary observer, and distances in the direction you are moving actually contract. These are not optical illusions or measurement errors. They are real physical effects. Time and space are not absolute. They are relative depending on your motion. The only thing that is absolute, that is the same for everyone regardless of how they are moving, is the speed of light. This has been tested experimentally countless times. Particles in particle accelerators move at speeds very close to the speed of light. We can measure how long they live before decaying. And we find that particles moving at 99.9% of the speed of light live much longer than identical particles at rest. Time is literally moving slower for them. This is not theory. It is measured fact. GPS satellites orbiting Earth move fast enough and are far enough from Earth's gravitational field that time dilation becomes measurable. The atomic clocks on GPS satellites run at a slightly different rate than identical clocks on the ground. If GPS did not account for this time dilation effect, your GPS navigation would be off by several kilometers within just a few hours. The fact that GPS works is proof that time dilation is real. Cosmic rays, high-energy particles from space, create muons when they hit the upper atmosphere. Muons are subatomic particles that decay very quickly with a half-life of about 2 microseconds. At this rate, even moving at close to the speed of light, muons created in the upper atmosphere should not be able to reach the ground before decaying. And yet, we detect muons at ground level all the time. Why? Because from our perspective, the muons are moving so fast that time dilation extends their lifetime. What is 2 microseconds from the muon's perspective becomes much longer from our perspective, long enough for them to reach the ground. Only massless particles like photons, which are particles of light, can travel at the speed of light. Photons have no rest mass, so they do not need infinite energy to reach light speed. In fact, photons must always travel at light speed. They cannot slow down or speed up. From the moment they are created to the moment they are absorbed, they travel at exactly the speed of light. No faster, no slower. This is simply what photons do. It is their nature. This has profound implications for space travel that go beyond just engineering challenges. Even if we developed perfect propulsion systems with access to unlimited energy, even if we solved every engineering problem imaginable, we still could not travel faster than light. The 4.24 light-years to Proxima Centauri represents a minimum travel time of 4.24 years, even in the most optimistic scenario where we could somehow accelerate a spacecraft to nearly the speed of light. And that is just getting to the nearest star. Most destinations in space are much, much farther away. Some science fiction proposes ways around this limitation. Warp drives that bend space around a spacecraft, allowing it to effectively travel faster than light without actually moving faster than light through space. Wormholes that create shortcuts through space-time, connecting distant points in space. Hyperspace, an alternate dimension where the laws of physics are different and faster than light travel is possible. These are creative ideas, and some, like warp drives, have a basis in theoretical physics. The Alcubierre drive, proposed in 1994, is a theoretical solution to Einstein's field equations that would allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. But there are problems. The Alcubierre drive would require exotic matter with negative energy density to work. No such matter is known to exist. Some physicists think it might be impossible on fundamental grounds. Even if exotic matter exists, you would need an enormous amount of it, possibly more mass energy than exists in the entire observable universe. And there are causality problems. If you could travel faster than light, you could potentially travel backward in time, creating paradoxes. Wormholes, if they exist, would likely be incredibly unstable and would collapse before anything could pass through them. Keeping a wormhole open long enough to travel through it might require more energy than exists in the entire universe. And again, there are causality problems. If wormholes allow faster than light travel, they also allow time travel to the past with all the associated paradoxes. Hyperspace is pure speculation with no basis in known physics. It is a science fiction concept that makes for good stories, but does not have any connection to real physics or mathematics. There is no evidence that any such thing exists or could exist. As far as we know, based on over a century of careful experiments and observations, the speed of light is an absolute barrier. It is not a challenge to be overcome with better technology. It is a fundamental law of nature. When we talk about stars that are hundreds or thousands of light years away, we are talking about distances that might be fundamentally unreachable with any technology that is consistent with the laws of physics as we understand them. The light year does not just measure distance. It measures a barrier, a limit, a boundary beyond which the normal rules of cause and effect start to break down. Let us talk about Proxima Centauri because it is our closest stellar neighbor and helps us understand these distances practically. Understanding Proxima Centauri, the closest star beyond our Sun, gives us a sense of what it means when we say even the nearest stars are impossibly far away. Proxima Centauri is a small red dwarf star in the Alpha Centauri system, which is actually a triple star system. Two of them, Alpha Centauri A and B, are Sun-like stars orbiting each other. They are similar in size and brightness to our Sun, and they orbit their common center of mass every 79.9 years in a slow gravitational dance that has been going on for billions of years. If you could see them up close, Alpha Centauri A and B would look like two suns circling each other against the darkness of space. Proxima Centauri is much smaller, about 1/8 the Sun's mass and 1/7 its diameter. It is so small and dim that you cannot see it with the naked eye. Even though it is our nearest stellar neighbor, you need a telescope to spot it. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, making up about 70% of all stars. But they are all so dim that none of them are visible to the naked eye, despite being relatively common. When you look up at the night sky, every star you can see with your naked eye is either larger and brighter than the Sun, or it is not a star at all, but a planet. Proxima Centauri is 4.24 light-years away, about 40 trillion 140 billion kilometers. That is 40 with 12 zeros after it. To put this in perspective, if you could somehow travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe at 192